1K. Okay. Then what is the average size of the index key entry? Average size of this one is 9 plus 6. 15 bytes. Which means divide by this. What is the blocking factor? So if you divide this one, it's a 68 point something. So which means it's a 68. In other words, you can keep the 68 key entry in one block. Each entry represents what? One block of the data file. It's anchor data. So then we can calculate the logarithm. We can calculate the block, number of blocks. How many blocks do we need? This one divided by how many blocks do we need? The block size is what? How many index? Hold on. This is the number of blocks, right? Number of blocks, so divided by 68, right? So that is a 45 block. We need a 45 block for index. And we have the 3000 block in a data file table. Okay, then we can do the logarithm. Logarithm, the log of 45 based on 2 is the 6th block. Okay, so which means for binary search of this one, it takes a 6th block. So how long it takes? 6 block plus, don't forget, this is important, we need to always plus 1 when we are using the index. That means even though you know the location of your friend or the room number, address, you need to go one more. So even though you find the location of 100, you need to go to the block, data block, one more IO. Always you need one more IO. So that is a 6 plus 1. Total how many? 7 block need. You can do 6 block, 6 IO plus 1, 7 IO. So compared to the binary search is 12 block. And the sequential search is the this one, the 1500. Which one is the best one? Using index. This one is the fastest one. Okay, so this is how to evaluate how much fast the indexing algorithm is. Okay, I'm not going to use the slide. The PPT file and textbook has this information. You can check. It's not very complicated algorithm, so you can check how much fast each algorithm is. So next one is this one is called the index level. If you take a look at index, how many levels? It's just one level. So it's called the single level index. So you can access the data. Index, data, one level, single level index. There's another type of the single level index which is called the clustering. In case, let's take a look at this data file. This data file is organized, sorted. It's an ordered file. Ordered by what? Department number. Department number of employee. Is it the unique or not?
No, it's not.
It's not unique, definitely. It's a group of data. Department number 1, department number 2, 3, so on. When you index non-key, it's not a key, but grouping data, you can. But this file is ordered by what? Non-key. Sometimes you can order your file by the non-key. Cluster. Cluster means a group. So it's a group data. You can select the 1 and pointer, 2 and pointer, 3 pointer, and so on. This is called the clustering index. Is it dense index or non-dense index? Non-dense index, because we have the 30,000 record, but we have only 8, right? So it's non-dense index. Is this single level or multi-level? It's also single level, only one level. Then how can we search the data? Exactly same as the previous one. Search by the clustering, the value, which means department number. Think about select the name from employee where DNO is equal to 1. If you are using this index, can we utilize this index for this query? No, there's no way, because the condition is DNO. You need to go to each and every one. It will take a much longer time. So we cannot use this index. Instead, if we have this clustering index, we can go to the DNO is equal to 1. 1 is the block pointer, then go to the data. Then we can access the data quickly. So this is called the clustering index. For example, non-key index. Sometimes, what's the difference between this one and this one? Both of them are clustering index, but this one and this one allow multiple value in one block. However, sometimes you don't want. At the time, you can allow only one unique value per block. So this is not much different. However, in this case, we can have the block pointer for the next and next. Okay, so this is the primary index, cluster index. Another type of general index is the secondary index. Secondary index is further using this one. This is a data file, but this is not ordered by the key. Okay, it's in terms of this value, it's non-ordered file. For the non-ordered file, I'd like to make the index. How can you do that? For each and every value, order. You don't have to put the other attribute, only this one. Index the attribute and order and point each block. It's a general case, right? It can be used for the index. In other words, secondary index. Actually, this file can be ordered file. Ordered by what? UBID, for example. Or the name, primary key. This one is, even though unique, it's not used for ordering the data file. At that time, you can make, for example, so in this case, the column name is UBID. is 10. You cannot use primary index, because primary index, let's say the name. So to speed up this query, you need to make another index. So for this, the UBID column and point. So this is called the secondary index, additional index. So secondary index is more general types of index. In case of primary, it was a non-dense index. It's shorter. Because it's already data file is ordered, we can take the anchor. However, this secondary index, you need to index each and every data because it's non-ordered. So is it dense index or non-dense index?
Dense index.
It's definitely dense index. Okay, then how can we evaluate? Same thing. We can calculate the number of blocks to access the index plus 1. Okay, then is it a single level or multi-level?
Multi-level.
How many level? Only one level of index. It's a still single level index. Okay, you can take a look at only index structure. So that is the single level index and the dense index for the non-key. You can actually evaluate. You can follow the direction. Please do so in your the electron. Why is faster than the binary search and so on. If you have any question, you can ask the next one. Then another example of the secondary index is, in this case, this the index column is non-sorted, non-ordered, but they are unique. So we can have one value for the block one way for index key entry. However, what if this column is non-unique? There are same value over here. So for this one, there are different approaches. This is one of them. So instead of, so we have the, because it's not, is it dense or non-dense? It's a non-dense because it has the number of like the 100, but it has only 7. Okay. However, how many blocks for each? Many. So we have the set of array of the pointer for each index key value. It's an array. So for example, sometimes you can see 100, 200 for 8. The computer 30, 31, 32, you can see it's a multiple pointer. So actually, this is not part of the index layer. This is a part of the pointers, array of pointers. Okay? So this is a non-dense index. Is it single level or multi-level? Don't confuse. This is still single level. Why? Because it's just for visualization purpose. This is actually inside the pointer is a group of pointer array. So it's a single level index for the secondary. In case non-unique. So this is a summary of the single level index. Okay? First, the primary is the ordered file and the unique. So we can have the non-dense index and then only use the anchor data, so representative data, and cluster grouping data. It's already sorted, so it's a non-dense index. Okay, so we can use the anchor data. However, secondary index is not sorted. So in case of unique, so it's a dense, and in case of non-key, it's a non-unique. So at the time, it can be non-dense or dense, but the non-dense is the answer, non-dense. Then problem is, we have millions of pages. So we have almost millions of keywords. So even though we build a single level index like the data file, so like the 30,000 index block, let's say we have. Even though we can use the binary search is log. This one based on 2. Even it takes a time, right? So how can it takes a time even to search in the index? It takes a time to search in the index to find the keyword. What will be the solution? We can make the index of index. Okay? So which means multi-level index. For example, this is an example of the multi-level index. You can see this is a what? Ordered file. It's a key ordered by the key. So we can have. So this is the what kind of index is this? It's a non-dense index, right? Because it takes only anchor data. Anchor data, non-dense index, and single level. But suppose that it takes a time. Low based on 2, it takes a time. Then we can build another index. At that time, another level index doesn't have to be dense index because the index is already sorted. Right? We can take only anchor data 2, 35, 55, 85. So we have, let's say that we have only one the block of index in the second level. How many blocks do you need to find the data in this example? How many blocks?
3.
2? No? 3? No, I don't want to answer. 4? Why 4? I direct here. It's a 3. So we need how many IO here? Only one block. 1. Using the pointer, we can directly access how many block? Second, 2 block. Then finally, we can have the pointer of the data file plus 1, 3. So always a 3. So that is a benefit of the multi-level index. Question. What if data size is bigger and bigger and bigger? So even this second level is huge. What will be the solution?
Another index.
Another level. So it can be many levels of the index. It looks like the what is this? It's a tree structure. It's called the index tree. Tree index structure. It's very popularly used general, not database, general application. How can we search? We can always start from top, going to. Then this one has the what? Index key and pointer. Using pointer, we can search the data block. So that is the tree. Okay. So I don't have to explain about the tree because we already did and we already learned. So this is the general tree structure. So tree is the multi-level index. I'm going to skip this part, but if you are interested in the performance of the multi-level, so you can do that. There's one slide I tried to introduce. It's a two-level dynamic multi-level index. Yeah. So finally, we can have such a index tree. Okay, don't be confused. This is not the binary tree, it's general tree, which means each node has how many? Number of index key entry, depending on what? Blocking factor. It's a blocking, actually this is like this one. A pointer, 1, 1, B, something like that. Depending on the block, the blocking factor, it can be many. Okay, so that is the tree data structure for indexing. How can you search? You can always start from top, going to the children, proper children, and finally the terminal node, leaf node, has the data pointer. Then you can access the data. How do you update? You need to search the node, the block that include the proper indexing type. If we decide that this one has the new data or the update data, you can do that. Insert. In case of full, you need to split. Okay? In case of full, you can split into two parts. Okay, like in this case, if you have the index block, you can split. You can do the split. Problem. Where is the search tree? So this one, problem. What will be the problem of the? So it will be fast. So we can use the search the tree to find the data block. Problem will be.
Block should be shorter.
Block will be.
Shorter
Access time. Access time is good, usually 3. It's the logarithm of the level, right? Traversing. But we can always start from the top. We don't have to that. 3 has always the same problem. Extreme case. It can be
One of the node is deleted.
in extreme case.
Skew.
This is also 3, right? Skewed 3. In case the tree is skewed, this is the same as what?
Linked list.
Linked list. Okay? It's a, but not binary search. This will be the linear search. It will be the same as the linear search. So I'm not going to explain the details, the tree structure for indexing because we don't use a lot. So instead, to address that problem, I'm going to skip this part. Oh, by the way, I'd like to explain the notation. Okay, just notation. So this is the schematic diagram to explain about the index tree. Okay, at this time, each block represents what? each node represent one block, indexed block. Okay, this is an indexed block. Then, how many index key entry do we have here? Index key entry. How many? Each node has how many index key entry?
2.
2. So blocking factor is a 2. Then what is the solid dot here?
Pointer.
It's a pointer for
Next.
child node, next level index block. Okay. Then what is the 5 actually?
Key entry.
Key entry, which means actually this one is the same as a 5 and data pointer, but simplify. So index is a secondary. Our goal is to find the address of a data block. So 5 has the data pointer, like this one. And 6 has the data pointer. So each index key entry has the data pointer, but sometimes simplify. That doesn't mean that we do not have the data file, but we have the data file. Always this is like this index key entry. At this time, the level order of this tree structure is called the tree. Tree means how many children node it has. For example, 1, 2, 3. So which means the search tree has a p-1 index key entry per node. Don't be confused. So that's the notation. Okay. So then arrow means it's nothing but pointer. Address of for example, this one is the address of this block. Block has the block ID number. So using block ID number, you can access the data. So that is the in case. So if I ask you the homework to implement the search tree, how can you implement? All of this is what? Index 5. It's a 5. 5 consists of what? Number of block 2, 3, 4, 5, 3. They are not sequentially ordered. It's a tree. So you can assign the block ID 0, 1, 2, 3, 4. It doesn't have to be the sequential, but you need to use that block ID as a pointer. Then finally you can implement. Like you can define the node index block class. Then instantiate every time. Then point. Or if you are using file, you can create the file whenever new index block is created. Okay, that is the search tree. However, as we have seen here, search tree has the problem of skew. In other words, it's unbalanced. In case of unbalanced tree, it will be same as the linear search. It's not convenient. It's not efficient. How can we address such a problem? It's unbalanced, so we can make balanced. So that balanced tree is the B tree or B plus tree. That is one of the frequently confused the thing. Whenever we are talking about the B tree or B plus tree in database, it's not the binary tree. Binary tree is in the data structure. It's a very special case. Okay? It's a very special case to understand the tree structure. In the database, B tree and B plus tree means it's a balanced tree. Then, question is, how can we make the balanced tree? What? Any answer? Any idea? How can we make the balance? New algorithm? So what kind of algorithm, right? So you can imagine, I think you are able to think, just think. So most of the time, whenever you are doing research or whenever you encounter problem, it's not only for this one, but any kind of developing. So you need to clarify what is the problem of this, why it happened. So tree, this search tree is basically how it is built. It's always top to bottom. Because of that, it can be bottom, 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 bottom. So it will be skewed, unbalanced. Then to address that, why don't we build the tree bottom to up? If we have the same bottom leaf node, always same level, right? We start the build upward from the bottom. Then each bottom will be the same level of the tree. Does it make sense? Yes, it makes sense. So instead of top to bottom, we are going to build the tree bottom to up. So that is the idea of the B tree index, balanced tree. So we will see such a balanced tree. To do that, to understand that the balanced tree, there are several operations you need to understand. First, node structure. We have seen in the search tree. This one is the indexed block. In terms of tree, this is called node. So this is an indexed node. This node has the number of index key entry, like the order P, which means like this one. This is what? Child pointer. Child pointer, child pointer, child pointer. Next level index block pointer. Each one has, this one is what? Index key entry. Okay? This one, index key entry, index key entry. This is a data pointer. Okay? We are going to use the same node structure as the search tree. Node was not problem. Problem is how to organize such a number of nodes. So we are going to use the same node. So for example, this is the P equal to 4. We can have. We are going to use the same, the node structure, entire tree. Then there's one operation. What is? We add the data, data, data. How many index key entry can this one have? 3. What if there's one more? So food. This is called the food. In case of food, what will be the solution?
Split the data.
We split the data. Based on what? Half. Medium data. Middle data. So that's called the, in case of food, split. 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 So divide into two. For example, we have 1, 2, 3 index key entry here. There's one more 4. How can you divide into 2? First, decide middle value. Which one will be the middle value? 2.5 doesn't make sense. So in our classroom, so we will select the cut in half left-hand side. It may be right-hand side. It's not wrong, but the consistency. So as long as constant, in this classroom, we are going to use cut in half and left-hand side. Select the middle value. In this case, 2. Then copy exactly same thing. And what will be this one is the left-hand side. Based on the middle value, left-hand side going to here. Then split. Based on the middle value, right-hand side, 3 and 4. Split into 2. However, where is the 2? We will, if you remember, bottom to up. So next step is promotion. Promotion means we will create upper level. Exactly same thing. So which one is the middle value? 2. Then the next thing is pointer. Pointer. So this one, point to this. And bigger than 2, point to this one. This is called the split and promotion. Using that split and promotion, we can bottom to up. Check. How many level? 2. How many level? 2. This looks like the simple. We will see more complicated case. That is where is the example? There's an example of this one. 8517. Let's use the so 8 5 1 7 3 12 9 6. Okay. So this is the index value. Actually, in real situation, it will be like the A, Lee, and address will be inserted. Next, 5, and the James, and the other address will be inserted. However, we will be only index to simplify. In the data file, entire row will be inserted. So this is the order of what? Only index key entry. In real situation, it will be number of 1, 2, 3, 4, 5, 6, 7, 8 record will be inserted in this order. Okay, so in this case, P is equal to 3. Then build the B3 index. Okay, first thing you need to do is decide the node structure. In case of P is equal to 3, how many index key entry?
2.
2. So we have 2. And this one is the data pointer. And how many children pointer? Next level pointer. 3. 1, 2, 3. We are going to use this node structure. And first, 8 is inserted. There's no available node we need to create. What's the value? 8. That's it. And next, 5 is inserted. 5, is there any space? Yes. So in 1, it's not a big, because it's one block in the memory, so we can quickly sort 5 and 8. Actually, don't forget there is pointer. What is this? Data pointer here. Like this one actually point 5 and lead and so on. 8 point this 8 James. Okay. So then after we insert this, the next one it will be 1. So I'd like to insert the 1. Is there any space?
No.
No, it's called the full of the node. In case of full, we need to
Split.
split. So we are going to